Hello everyone, welcome back to my YouTube channel. This is Xiaofu. I'm currently a staff control algorithm engineer in ASML. So in this current lecture, I'm going to teach you how we can derive transfer function, which is part 2. That is the continuing version from the part 1 of a quarter car model. And after that, we are going to derive the state space model of a quarter car system. Also introduce what are the fundamentals of state space model. And the last, we will also model the quarter car in MATLAB simulation and let you have a better understanding how the road condition change might impact the passenger comfortness. And in the next video, I'm going to discuss about the linearization of nonlinear system. As we mentioned, LTI system, state space model are all applied to linear system. If you have a nonlinear system, then how do we deal with it by using linearization approaches? If you really like my video, please subscribe to my YouTube channel. Also, in an additional series of videos, I'm also going to share my knowledge, experience on how you can start your own tech startup company, starting from your PhD thesis. I hope that will also give you a different or separate insights. So back to our part 1. So in part 1, we use the sprawl mass translate from time domain to Laplace domain, and then we derive the relation between the sprawl mass and unsprawl mass. So right now, if you look at the unsprawl mass differential equation, if we translate into a Laplace domain, so as I mentioned in the last video, if you have first order derivative, then that will become s to the power 1 times the variable itself in Laplace domain. If you have second order, then you have s squared times the variable in Laplace domain. So using this approach, if we can quickly derive the unsprawl mass is Laplace domain. So keep going. So the very first row is the Laplace domain of the unsprawl mass representation. So as we already know, the relation between unsprawl mass and sprawl mass from the last video, so you simply plug your unsprawl mass. If we go back to the previous slide, you can see z mu of s, the last equation, equals to this let's say coefficients times z s of s, right? So go back to the equation right now showing on the second row. You can see z mu of s. We just substitute with the this chunk of coefficients that is represented by z s of s. And after that, if you look at the third equation, you will see the entire equation is only a function of zs of s and also z0 of s. So our initial goal is to derive the transfer function between z0 and zs, right? So now we are very close to the final step. Then what we need to do is to make sure we factor out or move all zs term in one side and z0s in another side, and then you get the fourth equation. So the fifth equation, what we are trying to do is we factor out all these coefficients, and then for different order of s, so we start from highest order s to the power 4, and then to the power 3, to the power until 1. So we actually factor out every correlated coefficients for different order or different power of s. So after we have done that, so we can then, for the last equation, so those are already known parameters. So then we combine all those known parameters, define them as a new variable. So after that, as you can see, we reach the final equation, which is the final transfer function between output zs of s and the input z0 of s. And now let's introduce, now we finished the transfer function derivation, and let's introduce what are fundamentals of state space. So simply speaking, so state space create n first order differential equations out of an nth order differential equation, right? If you have a fourth order differential equation, you will create 4 first order differential equations. So that means state space model has to be based on first order differential equation, right? So then also state space model must be in the following form, where you have your state vector, input u, output y. And so if you look at this more carefully, a state vector is a collection of variables, such as given an initial condition, your initial state, and your input u, at any upcoming time, it is possible to predict your state response. So how we derive the state space representations, it's not that difficult. So if you look at it, we summarize that into 3 different steps. Step 1, you write your equations of motion for each degree of freedom, right? And choose the corresponding state variables. If an equation of motion is first order, then no matter what variable is being differentiated, should be a state. If an equation is, let's say, higher order, right, than first order, there should be as many states as there are derivatives. Let's say your highest derivative is second, right? That means you have a second order system. Then you should have 2 states. And then rewrite your dynamics entirely in terms of all the states and inputs, which will get you in the following format: x dot equals to f of function x comma u, or x of dot equals to ax plus bu, y equals to a function g of x and u, or namely y equals to cx plus du. So if we go back to the quarter car example, right? So if you look at your quarter car example, so let's go back to the free body diagram and those initial equation of motion we derived. So for sprung mass and unsprung mass, those 2 are all second order differential equations, right? The highest order is 2. So that means each one of them you should have 2 states. So in total, 2 plus 2, you should have in total 4 states. So that means you have 4 first order differential equation, right? In your state space model. And then let's go back to your quarter car model again. Let's follow the steps that we just summarized, then derive the state space model. So quarter car and this quarter car model will have sprung mass and unsprung mass, right? Each one of them are all second order. So let's define x1 is z of s, which is a displacement. x2 is z of s dot, which is a velocity. So similarly, we did the same thing for unsprung mass, right? If we recall our equation of motion from the previous one, so let's go back to the previous one, right? If you go back to the previous one, we can see that we have second order z of s double dot, right? Z of s dot is x2. So z of s double dot is x2 dot, right? So if we go back to here, then we will be able to translate it quickly. So let's right now assume that the damping for the unsprung mass is 0. Otherwise, it will have a nonlinear term eventually in the state space model. Let's assume that. So if people are interested, so we can also have a separate video to discuss how we deal with the first order, or derivative that are showing in the state space model, how we can deal with it, eventually make your state space model possible to be represented. So for now, let's assume it is 0. So like I mentioned, if we plug x1, x2, x3, x4 into the equation of motion, then this is those 4 set of first order differential equation you are going to derive. So as I just mentioned, zs double dot is x2 dot, right? So whenever you have your displacement term, then you use x1, x3. As the damping is associated with the second order, it's associated with the velocity term, so you can use x2 and x4. Similar, you do sprung and also unsprung mass, which is straightforward and simple, right? So here, after you have done that, let's list out those 4 differential equations in the sequence. So you say x1 dot equals to x2, right? So then on the very left hand side, so this x dot equals to a times x plus b times u, right? Let's use a times x is your state variable. As we defined, we have 4 different state variables, x1, x2, x3, x4. So let's write them in a row column. So then this is your state vector x. So then for each row is your first equation, right? Your x1 dot, if you look at it, if you have enough linear algebra knowledge or background, so you can say x1 dot should only equals to x2. Then we should have 0, 1, 0, 0. So that means x1 dot equals to 0 times x1, 1 times x2, right? So you should only have x2 term over here. So similarly, you should do the same thing for x2 dot, right? x2 dot, if you look at it, what is your x1 term? Your x1 term should be minus 4 times ks over ms, right? So following the same approach, you should write the row coefficients for the A model. So following the same format, you can do it for x3 dot and x4 dot, right? So then you have a times x term. So your input, where is your input? So your input here will be considered coming from the road, right? So which is z dot was 0, 0. So looking at your equation of motion, where is z0 showing up? It's only showing up on your unsprung mass, because unsprung mass is the one directly touching the ground or the road, right? So if you look at it carefully, you see z0 is associated with, let's say, associated with only k of t times 4 over m unsprung mass, right? So then as it is only applied on x4 dot, so that means you have 0 for the first 3 states. So after that, you have x dot equals to ax plus bu, all are represented in either matrix form or vector form, right? And then for us, we don't have output input. We don't have control input that are going into output. So your d should be 0. So you should have 0 term for your d. So d times u is essentially here you can consider 0. And generally c times x is your output. So your output matrix also depends on your sensor measurements. Let's say right now we only measure the displacement of the quarter car model. Then we should only have 1, 0, 0, 0 times your x. X is your state vectors. So x1, x2, x3, x4. So now, after we have seen the way how we derive state space model, like I mentioned, so we are also going to use a MATLAB simulation to look at how the quarter car model look like. So here in this MATLAB simulation, I have defined those variables, and also what I did is I my total simulation time is only 4 seconds. So at between 0.5 and 0.6 second duration, we introduce a bump, which is let's say a step response for our quarter car model. And then from 2.5 to 2.6 time duration, we introduce another bump over there. So that will be considered as a second disturbance. And we are using ODE 45 to solve the equation of motion, and we can look at the time response. If you like it, let me know. I can also share the MATLAB file in the future if people really like it and want to know how I make this model. So if you run it, let's say I have plotted two different time response. So one is suspension travel, another one is a sprung mass travel. As we know, we only introduced two different road bump, right? So the sprung mass travel can be a metric used to evaluate the passenger comfort needs. And as you can see, the suspension model is the one, suspension travel, sorry. The suspension travel can be from 7 centimeter to let's say damp to a little less than 7 and eventually damp out, right? So if you have, let's say, a larger one, 7 centimeter bump, your suspension travel can be as large as close to, let's say, almost 10 centimeter, right? And then let's look at your sprung mass travel, which means the passenger side. So as you can see, even though the road have 5 centimeter bump because of the damping, and it only traveled maximum to close to 0.03 centimeter, right? And similarly, if we introduce a 7 centimeter bump, it only travel as large as only 4 centimeter. So that means the sprung mass travel, if it is smooth enough, has much less disturbance, then in that sense, you might need a controlled performance that you can react to this disturbance and can make the disturbance be cancelled very well. Then in that sense, you will have a very good passenger comfort needs. But in this one, we don't really have any control over there. It's just a simply simulation of a quarter car model response to the road disturbance. So that's why in the future, if people are interested, we can add probably PID control, starting from PID control to show you how we can make sure the disturbance can be cancelled out effectively so that the passengers sit in the passenger side don't feel the disturbance much. So where a lot of luxury cars have this supreme feature to make it very comfortable. Okay, everyone, thank you for listening. This is everything that I'm going to share for this video. If you like it, please subscribe to my YouTube channel. That will motivate me to make even more videos. Thank you.